Hello, this is Raf Alvarado. Welcome to Exploratory Text Analytics. In this video, we're going to look at the concept of similarity, especially as it applies within vector space. So remember that we were looking in a previous video at the concept of a document term matrix or a word context matrix that we got by converting our token table into a bag of words, and then by taking that bag of words and unstacking it into a full-blown matrix. And we end up with something that looks like this, where we have on one axis our terms, our vocabulary, and on the other axis our documents, which we represented as an ordered hierarchy of content objects index in our pandas data frame. Now, the thing to realize is that this matrix consists of a whole bunch of pairs of vectors. So along either axis, either the terms axis or the document axis, we can compare any two vectors to each other and come up with a mathematical understanding of their similarity. So I have down below just a couple of arbitrarily chosen vectors. They're term vector 2 and term vector 8, document vector 1 and document vector 4. And if you look at the numbers, you can imagine that there are various ways that you could compute how they're similar based on how the two sets of numbers stack up, as it were. We're going to look more specifically at how these operations work. So remember that one of the great advantages of the vector space model is that it allows us to find similar documents and words based on these pairs. And so some of the key use cases here for this kind of operation where we're looking for similarity among documents is that we can do things like standard query matching, which is searching to find documents that match a search. So you can take a search string and treat it as a kind of document and find what's the closest document to the search string. Or we can say, let's find all the documents that are close to each other based on some parameters and group them. That's called clustering. Or we can summarize documents based on their possession of similar contents. We can also flip things, and we can talk about word vectors. We can say, okay, which words are closest to each other in vector space? We might have some threshold by which we define a synonym, and then we can branch out and talk about word networks that characterize large corpora. This actually is very useful to the work of text analytics, exploratory text analytics as we're defining in this course, because it actually provides some insight into the cultural and psychological underpinnings of these texts. But to do any of this stuff, we have to drill down and understand this fundamental concept of similarity. So let's get right into it and get to an understanding of what precisely is similarity. So let's look at one of our example representations of vector space. Here is the Jane Austen's Persuasion represented in vector space, where we've picked out 3 of the dimensions from that space. You remember each term is a dimension, so we have the dimension of Anne, the dimension of Wentworth, and the dimension of Spoke, and we can plot the documents, which are chapters, in this vector space. And you can see that the intuition here is that in this vector space, we want to say that the dots that are the points that are close to each other are more similar. In other words, that the contents of chapter 8 and chapter 19 we want to think of as more similar to each other than the contents of chapter 9 and chapter 17, which are more distant in this space. This is the basic intuition of how we think about similarity within vector space. So this is essentially a variant of the statistical semantics hypothesis that we looked at, that Turney and Pentel introduced. Perhaps we might call it the geometrical semantics hypothesis, because what we're saying is that meaning is correlated with geometry. What this means is that the notion of similarity that we're working with is based on the metaphor of space, of geometric space, and whereby similarity is thought of as what is proximate in vector space, and distance is just distance in vector space. These two correlative terms, similarity and distance, are both expressed as functions of vector pairs. So typically similarity is expressed in the following way: sim A and B, where the output value is going to produce a number such that a greater number means things are closer, and therefore more similar, whereas distance functions you usually write as DAB, as shown, where the output value is a number which is greater, which, if greater, means that the two things are farther away and therefore are less similar. Many of the functions there are many functions, I should point out, that have been developed for each of these measures, and we're going to go into a few of them in this video. So here are three of them. We're going to see this slide again after we've looked at what these things mean. But these are the three probably are the most common measures looked at in two-dimensional space. You'll see here that we have two measures of distance and one of similarity. So Euclidean and Manhattan distance measures are as shown here. Manhattan distance, the reason it's called that is because it looks like you're driving in Manhattan, or sometimes it's called city block distance or taxi cab distance. You go along the distance of each axis or each dimension, whereas in Euclidean distance you're taking the hypotenuse of that right triangle that's being formed by the two other dimensions. We'll look at how to compute this mathematically in larger spaces than 2 dimensions. In a sense, I think it's helpful to understand some of the semantics here. Distance is the more fundamental concept of the two. Because in everyday speech, what we mean by similarity is that similarity is a qualitative comparison between two things. We say, oh, this book is very similar to that book. Maybe deep down in our brains there's some mathematical operation going on that has something to do with this, what I'm calling the geometric semantic hypothesis. But really what we mean is we're not quite sure why we think things are similar. We just say that they are. Whereas distance is more precisely a quantitative measure of space between two things. And what we're doing when we're talking about similarity and distance metrics here is we're really collapsing similarity onto distance. As I've just shown, similarity is thought of as proximity, as closeness, or as difference is thought as distance, which is the opposite of closeness, even though we use the word distance to stand for the general thing as well. So let's look at what we're talking about here, a couple other properties of similarity and distance measures. First of all, in vector space, it's helpful to know that similarity is transformable into distance and vice versa. It's often expressible as the inverse of distance. Here we have similarity of A and B, two vectors equals 1 over the distance of A and B. This sometimes is expressed as 1 over the distance of A and B plus 1 to avoid division by 0, where A equals B, because one of the properties here of distance measures is that if two things are identical, they have a distance of 0. Distance as a metric is subject to something called the triangle inequality law. We can actually see that this applies to certain measures of similarity that don't meet this law. Here the law, I'm just trying to describe it here in terms of this triangle. The distance between A and C, which is the hypotenuse, is always going to be less than or equal to the distance between A and B plus the distance between B and C. So you can imagine if B got closer and closer to the line between A and C so that it stopped being a triangle and was just flat, you would see that A plus B is AB plus BC is equal to AC, but it can't ever get smaller than that. The other property of a similarity and distance measure is that they have to be symmetric. So we want to say that the distance between A and B is equal to the distance between B and A, and we want to say the same thing about similarity. So there are many, many measures of distance and similarity, as well as other measures called divergence that we will look at. It's a related concept. And I like to group these. There are a whole bunch of them. If you go to the literature and if you look at the readings I provided for this session, you'll see that there's just lots and lots of different measures. And I think one good way of thinking about how these break out is in along two axes. On the one axis, you have the difference between similarity measures, distance measures, and divergence measures. And on another axis, you have the difference between the kind of matrix that these measures are being applied to. So we've talked about three kinds of matrices, or we can talk about three kinds of matrices. We've seen two ways of doing this in the previous module. The first is we can talk about a matrix, a document term matrix of binary counts. And what that is a matrix where every cell is occupied by either a 0 or 1, and all we're concerned about is the presence or absence of a term in a document. For those kinds of matrices, the best measures are based on set theory. Now, the second kind of matrix is the most common, what we begin with when we take a bag of words and we unstack it into a document term matrix. These are what I call raw count matrices, and they are best measured, distance between vectors in that space are best measured using linear algebra and geometry, the way that we've looked at so far, the Euclidean and the Manhattan distances, for example. And then we have a third kind of table, which is a normalized table where we take a document vector, for example, and we divide all of its values by the sum so that each cell, each item in that vector is a percentage. So we can say that the word the takes up 20% of the document, the word car maybe takes 5%, and so forth. And what we want to do, what you'll find as a property, is that the sum of all the terms in a document should equal 1. So that's a probability vector. And when we have our matrix in that form, we are able to use measures based on information theory. In all three of these cases, we can use all the different measures, but these are the measures that make most sense given the kind of matrix we're working with. And I just want to quickly remind you of where we are in our workflow to where we can get to these three kinds of matrices. We begin with a token table, which we did last time, and we apply a group by operation to produce a bag of words. And then with the bag of words, we can unstack it into a document term matrix, which is also a word context matrix, depending on how you look at it. And then with that matrix, we can normalize it in various ways, which we did for term frequency and versus document frequency. We saw that there are different ways of normalizing or standardizing each of the vectors that we are the term vectors that we're looking at. But we also can do these other kinds of normalization that we haven't talked about so much. We certainly haven't talked about normalization per se. I'll mention something about that in this video. But we can think of taking the counts of terms in a document term matrix such that we convert arbitrary real numbers into binaries as a form of normalization. And then we can also think of converting a vector into a probability vector, as I just described, as a kind of normalization. So we have those three kinds of normalization that we can perform. And then on each of those, we can perform different kinds of weighting. So we've looked at removing non-zeros. We focused specifically on TF-IDF last time. We didn't look at point-wise mutual information, which is talked about in the Turnian-Patel piece. But you can think of that as another kind of weighting that's appropriate to this particular kind of matrix, a probability matrix. So for each one of these kinds of matrix, we can have, we can see that there are optimal measures. Here I've just organized it into a 3x3 table to get the point across. And I think this is very helpful in organizing all of these different measures, because if you're reading the text that I've given you, you'll see it's going to look like a kind of a hodgepodge. No author really seems to have sort of, taken the time to sort of pull them all together. There is one piece that I've given you to read by Cha, piece published in 2004, which shows you all the distance measures, but that's quite a bit that is presented in that piece. And she groups them into families. Anyway, let's look at some of these distance measures. So let's look at count distance measures. These are probably the most common because the count matrix is probably the most common matrix to begin with anyway. The most simple kind of measure that we can use in comparing two vectors is Manhattan distance. We've already seen that graphically, and that's basically where you just sum up the differences between the elements of each vector. So element 1 in vector A minus element 1 in vector B gets added to element 2 in vector A minus element 2 in vector B. So you're basically summing the differences. In a way, Manhattan distance is what you might just call the difference between two vectors. Euclidean distance is pretty much Pythagoras' theorem that we all learned in geometry, put to the nth dimension. So instead of just 2 dimensions, we can go to n, and all we're doing is just taking the difference, as we did before in Manhattan distance, and squaring that. And then once we've summed up all the squares, we reverse that operation and we get the square root. That is actually, as you can see, both of the preceding Manhattan and Euclidean are just special cases of a more general rule specified by what is called Minkowski distance. And in Minkowski distance, the distance between two vectors is where you take the absolute value of the difference between the element pairs and you raise it to a power, and you sum all those, and then you get the power root of that summation. So you can see that in Manhattan distance is where p equals 1, and Euclidean distance is where p equals 2. This is a very powerful formula. It can be expressed up to infinity, and p might even be fractional values. We'll just look at, we'll move on, instead of looking at those, onto count similarity measures, which are also extremely popular. The first one that is, the easiest to compute is just the simple dot product. I can take any two vectors and multiply them by each other. Remember in vector math, if you multiply two vectors, basically you're just summing each element pair multiplied, and that's it. And simple dot product is a useful measure, but it produces an unbounded value. In other words, different corpora are going to have different maximum values of distance. It's hard to get a sense of what these distance measures mean. You have to do some statistics on all of them and so forth to get a sense of what's going on. But also, most importantly, this raw measure just favors long documents. Documents that are about the same thing, but if they're of different length, they're going to appear as different in this measure. So what we have is something called cosine measure, which is essentially the dot product divided by the norms of the two vectors, and we'll look at what the norm is in general. But you can see the formula here in the middle. You're basically just summing the product of each element pair, and then you're dividing by the product of each element pair individually, squared and square rooted. This is a better metric. It returns a value between -1 and 1. If all of our input values are greater than 0, however, or if they're non-negative, which is the case with our term document matrix, then it returns a value between 0 and 1. So this is very nice, because what it does is gives you a nice number that's easy to compare, that you can easily define a threshold for example, so that if it's 1, it's maximally similar. If it's 0, it's dissimilar. And this is where we get the expression orthogonal, because two vectors which are orthogonal, like imagine in two-dimensional space, if they are 90 degrees from each other, if you multiply them, they will produce 0 as a value, and that means that they are orthogonal. So orthogonality means they have nothing to do with each other. Two ships passing in the night. This metric, cosine similarity, is extremely popular, and oftentimes it's written using the formula instead of sim. It's written as cosim A and B. There's lots of variation in that notation, however, in the literature. So here we are looking back again at the different kinds of distance, and here I've associated the visual representation of each kind of distance with the mathematical formula. Note that the cosine similarity is really the cosine of that angle between two vectors. So the cosine of that angle turns out to be very easily expressed in vector math as the dot product of two vectors divided by the product of their norm. So looking at binary similarity measures, these are essentially set theoretical operations. If you want to use what's just called the simple matching coefficient, what you begin by doing is taking all the non-zero values in two vectors, and you just get the intersection of them. So you can imagine two documents that don't share any words, are going to have no members in the intersection, so the absolute value of that is going to be 0, whereas two documents that have, words in common, many words in common, are going to, have some positive value. Again, this is an unbounded value, and it privileges vector length again, so we want to normalize it. And the one typical way of normalizing the matching coefficient is what's called the dice measure of similarity. And there you simply double the intersection, the norm of the intersection, and you divide it by the length of the two vectors independently. Another measure in this category of binary similarity measures is the Jacquard measure. This is a very intuitive one. Basically what you're doing is saying divide the number of terms that two documents share by the total numbers that the two documents possess in aggregate, the intersection over the union. And that's a very intuitive understanding of similarity. We can say that two documents probably have something in common if they share a lot of words relative to how many words they actually have. And here, remember, we're talking about, since it's set theoretical, we're talking about distinct values of words. So the intersection between two sets is going to be the elements of those two sets in common, but not repeated. So the third category of measure is what we'll call the probability divergent set of measures. And these are applicable to document term matrices where the values are expressed as probabilities along the vector of interest. And there's a term that's been developed called divergence in this field, and this follows from information theory, which we talked about a few modules ago. And the notation for talking about representing divergence is that double bar, D with the A and B separated by a double bar. We often use the subscript, here we have KL and JSD, to distinguish between kinds of divergence measures. And by the way, we can do the same thing with the similarity and distance measures if we want. Oftentimes sim or D are subscripted as well to denote this particular kind of metric that's being used. So here we can see that this is what we saw in our lesson on entropy and information theory, that the Kullback-Leibler distance is the probability, if you will, of A times the log of A over B. And then Jensen-Shannon divergence is just a way of normalizing that because this metric is asymmetric. So it doesn't meet the criteria that we saw earlier for what a distance metric is. So that's why it's called divergence. So one way of thinking about all these different measures is that we're basically doing the same thing every single time, but we're just changing a couple of the operations. So we essentially take two vectors, and here I have two arbitrary vectors A and B that go from 0 to 11. They each have 12 elements. And in each case, you'll notice that what we're doing is some operation on each of the pairs. So AO, BO, A1, B1, A2, B2. They may get multiplied. They might get squared. You might get the absolute value of their difference. Something like that is applied to each element pair. And then an operation is applied to all of those results from each operation, such as summing, which is typical. And then you can take that result and normalize it or what have you. But basically, they're all doing the same thing. And so you can imagine you can come up with lots of different similarity and distance measures just by playing around with the possibilities here. Key idea that I want to mention in passing, it comes up a lot, and we've mentioned it already in this video, is the concept of normalization. It's a very simple concept. To normalize a vector is basically to divide each element of a vector by its length. The length of a vector is also called the norm of a vector. It's a useful operation when we want to discount length. For example, when we're comparing documents, one of the issues that comes up right away, we've already mentioned it a few times, is that documents differ in length. So we don't want to use measures that make a big deal out of that difference. Maybe sometimes we might, like if you're comparing War and Peace to a Hemingway short story, there probably are some differences that are going to derive from length. But the typical variation in length among documents in a corpus are not what we're looking for when we're talking about similarity. So we want to discount those. And that's what normalization does for us. The trick is that we can use different ways of normalizing because there are different ways of measuring the length of a vector. Just as we saw with the different kinds of distance measures, there are different kinds of length measures. L1 length is often called Manhattan length, just as we saw with Manhattan distance. And it's just the sum of the absolute value of each element. L2 is Euclidean, which is the square root of the sum of each element squared. And you can see that what's going on here is that this is a special case of a distance measure, because all we're doing is taking the distance between a vector and 0, which is the vector all of whose element values are 0. So we're essentially getting distance to 0 to define the norm. And just as there are many distance measures, there are many length measures for vectors. And just as we saw a generalization of distance, here we see a generalization of norms, and it's pretty straightforward. We can, again, P can be very large, and P can even be fractional. So if you use a norm other than, say, L1, you can determine whether you've done it properly by taking all of the normed values and raising them to the power that you normed them by, and that should equal 1. All right. So in summary, the most common measurements in text analytics are the following. So for measuring distance, it's typically Manhattan and Euclidean measures that are used. And for similarity, the most common by far measure is cosine. And if you're working with binary, Jacquard is very popular. And if you're working with probabilistic, Jensen-Shannon, again, which is just a normalized version of Kullback-Leibler, is used. Among these, cosine similarity is often used. It's really popular because it's already normalized for length. Remember, Euclidean distance and other forms of distance on non-normalized vectors is sensitive to length, so two documents will rank as dissimilar if they discuss the same content but have different lengths. And also notice that the cosine similarity is equivalent to the dot product of two normalized vectors. So what are some tools you can use, which we'll go into in our code workbook, to determine distances from the matrix? Here are 4 methods that are available from 4 different libraries. Actually, there are more methods here, but 4 different libraries. So NumPy, which is the foundation of our stack, which is basically Python's linear algebra library, has a method or a function called norm, which takes as an argument a vector or a matrix, and it returns the norm. Note, though, when you pass a matrix to it, it returns a single value. It's getting the full matrix norm, not the norm of all the vectors in the matrix treated individually. That's what scikit-learn preprocessing normalize does, which I have in the 3rd option here. A very useful set of functions is pdist and squareform from SciPy. So SciPy has a distance library that gives you all kinds of distances. If you go to the help page, you'll see that it includes the measures that I have here, plus a lot of others. Squareform is an important function that you need to convert the results back into a matrix form. But we'll look at these in more detail. Now, pandas also has some convenience functions like the correlation and the covariance function, which are 2 statistical ways of determining similarity between vectors, which we haven't gone into. But these, in my experience, are pretty slow. And we'll typically be using the SciPy spatial distance library to compute pairwise distances among vectors in vector space.